we have seen before in chapter 4 about the magnetic field at a very large distance from the center of a current carrying circular loop. And if this point P, let's say it is a point on the axial line, which is at the distance r from the point P, and when this point P, right, it is at a far distance from the center compared to the radius, then we have the expressions of the magnetic field B at this point, it is equals to this much. Okay, mu naught I a square upon 2r cube, where A is the radius of the circular loop and r here it stands for what? The distance of a point P from the center of the circular loop. Alright, now I will modify this equation in this way. That means I will multiply and divide, by 2 pi. You multiply the numerator by 2 pi and you divide the denominator by 2 pi. So when you multiply and divide by the same quantity, then the equation remains unchanged. So after that, right, I can say this is equals to mu naught 2 times 2, 4, mean 4 pi. And then I, this is I, and then I'll write first, I'll write first this factor 2, so this is I, and then I'll combine pi a square in this way, upon r cube, or B is equals to mu naught upon 4 pi 2 I. Now what is this pi a square? So pi a square, it is the radius of the circular loop. It is the area of the circular loop. So for the area, let me represent this area as capital A. So instead of pi a square, I will write capital A and then r cube. So this is my equation 1. So similarly, if you remember in chapter 2, we have also talked about the electric field at an axial point, which is at a very large distance, or at a very far distance from the center of the electric dipole. Okay, so in that case, we found that the electric field E at this point P from this electric dipole, and if this point P is at a very large distance, then this is the equations of the electric field at this point P. Okay, we have 1 upon 4 pi epsilon naught 2 P upon r cube. Okay, so let us name this as equation 2. Now this P here, it is known as electric dipole moment. Okay, alright. So comparing the two equations, equation 1 and equation 2, when you compare, you will find that the constant in equation 1 is mu naught upon 4 pi. The constant in this equation 2 is 1 upon 4 pi epsilon naught. We have here factor 2, we have here factor 2, and here this is r cube, this is r cube. Now if this P in equation 2 stands for electric dipole moment, so it means that this IA, right, should represent the magnetic dipole moment. So therefore, I say that the magnetic dipole moment which we usually denoted by letter small m, is equals to I times A. So this is now becomes the new equation for the magnetic dipole moment of a circular loop. So please remember, right, we obtain this equation by just comparing the magnetic field and the electric field at a very far distance from the center of the loop, and in electric field from the center of the electric dipole. So this M is equals to IA stands for what? the magnetic dipole moment of a current carrying circular loop. So therefore, because of this equation, I can see here that this current, which, this loop which carries a current, in this case, it behaves like what? It behaves like a magnetic dipole because of the same expressions of the electric field and magnetic field in the two cases. Okay, so please note down this equation. The magnetic moment of the current carrying circular loop is equals to IA. Alright, now in vector form, right, if you write m arrow, because m, it is a vector quantity, so it has a direction. So any quantity which has a direction can be written as, with that representation, okay, together with the symbol on top of together with the arrow on top of that letter. So in vector, I will write m arrow is equals to I a arrow. When I say a arrow, it means it is equals to a times n cap. Okay, so this n cap, it is, suppose if this is my circular loop, so n cap means it is the normal which is perpendicular to the plane of the loop. Okay, so in vector form, this is the equations of the magnetic dipole moment of a current carrying circular loop. And the directions of this magnetic dipole moment of this current carrying circular loop can be found by using Fleming left hand rule. So this is my, Fleming right hand rule. So this is my right hand. If the current in the loop, let's say it is flowing in anti-clockwise direction. So if the current I, it is in anti-clockwise direction, then my thumb, right, which is pointing outward, so this thumb will represent the directions of the magnetic dipole moment of a current carrying circular loop.